I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die.
Our next speaker, Dr. Pascal Lee, is a planetary scientist at the Mars Institute, the SETI Institute, and NASA Ames Research Center. He is internationally recognized for his work on the history of water on Mars, on the origin of Mars's moons, and on our subject tonight, planning the human exploration of Mars. Pascal earned a bachelor's degree in physics and a master's degree in geology and geophysics from the University of Paris. After coming to the US, he earned an astronomy PhD at Cornell, where he was able to work with Wonderfest inspiration and my personal hero, Carl Sagan. Dr. Lee has led over 30 expeditions to the Arctic and Antarctic to study Mars by comparison with the Earth. Dr. Lee recently finished his first book, Mission Mars, and his first major movie documentary, Passage to Mars. Please join me in welcoming Dr. Pascal Lee.
Thank you so much. It's a pleasure to be here. I came, thank you, Tucker. And again, Wonderfest is amazing, and thank you also to the California Academy of Science. I came here tonight with my dog. His name is King Kong. He's trained as a polar bear guard dog in our research projects at high latitudes in the north, of course. But he's actually technically an Australian cattle dog, so with training you can do anything. So tonight I'm going to talk to you about the what, why, how, when, and who of a human mission to Mars. And I have to move ahead quite quickly. There's more detail behind all this, but the point, though, is to convey that there's actually quite a bit of work going on to make this happen. And most of you, based on your good physical shape, should be around to see this. At least the first steps that we will be taking in the next decade or two. So without further ado, I'm going to talk to you about what is a human mission to Mars to begin with. So we don't have that many options. We are on this third rock from the sun. We've traveled to the moon, and the next planet that we could go visit would be either Venus or Mars. Venus is out of the question, even though it's closer to the Earth in size. The temperatures at the surface are close to 495 degrees Celsius, so that's what you have inside a good pizza oven. The atmospheric pressure is crushing. It's 90 bars, so that's what you have inside the sea at a depth of about 2,700 feet, almost 3,000 feet. Okay. The atmosphere is made of CO2, and there are clouds of sulfuric acid, H2SO4, raining down. It's a good depiction of hell. Mars, in contrast, is lethal, but it's less lethal. You will die in a more unusual way. So let's go see Mars. First of all, how far is it? At the top here, you have the Earth-Moon to scale. And so people sometimes are surprised to see how far the moon actually is. But with a conventional rocket, like a Saturn V rocket, chemical propulsion, it takes you about 3 days to get to the moon. If you don't do all these loops, you can spend as long as you want on the moon. And then it takes another 3 days to come back. So you could leave for the moon on a Monday morning, get there by Wednesday night, visit the moon Thursday all day, and then Friday morning, you catch a flight back to the Earth. Sunday night, you're back on Earth. Monday morning, you're back at work. All right. Mars is a different story. At the bottom here, I show you the Earth going around the sun. That's the blue orbit, with the moon very close to the Earth. Mars is going around the sun, of course, but on a wider loop, and it's also traveling more slowly. And in fact, the Earth is passing Mars once every 26 months. That sort of defines the duration of the interval between launch windows. When the Earth and Mars are on the same side in relation to the sun, the distance drops to about 55 million kilometers. But when Mars and Earth are on opposite sides of the sun, that's when the Earth-Mars distance becomes about 400 million kilometers, 1,000 times then the Earth-Moon distance. So if you go to Mars, at some point you're about 1,000 times farther away from Earth than if you were on the Moon. So going to Mars is definitely not just the next step beyond the Moon, it's quite a leap. And in terms of radio signal travel time, when you are close to each other, it's 3.5 minutes each way. When you're on opposite sides of the sun, it's 22 minutes, okay, each way. So a hello from Houston will take 22 minutes to get to you on Mars, and you might say, huh, what? And then that will take 22 minutes to get back to Houston. You can see how autonomous you will want to be on Mars, unlike on the Moon. Now, this is from my little children's book, but it depicts the travel time. So you depart the Earth, where it says start here. It takes you with early nuclear thermal rockets or high-performance chemical rockets about 6 months to get to Mars. Once you get to Mars, you cannot come back cheaply immediately. You have to wait for the two planets to reposition themselves before you can travel economically back to the Earth. So that means you have to stay about 18 months on Mars. And then you take your trip back to Mars, and it's another 6 months to cruise back to the Earth. So altogether, if you read the bottom, it's 6 months plus 18 months plus 6 months, about 30 months, 900 days, 2.5 years. It's a long time, but not that long. At the very top, you have cosmonaut Valery Polyakov. He was a medical doctor, a physician. He currently still holds the world record for the longest single space flight. It took place on Mir. He spent 437 days and 18 hours. That's 1.2 years. That's the longest single continuous flight. The most time spent in space by any human being was spent by Gennady Padalka. The record was actually just established in 2016. He spent 2.4 years of his life in space. And then the longest US space flight is held by, the record for that is held by Scott Kelly, who spent in one flight 0.9 years in space. Okay? So we're not quite at the point where we've done a 2.5-year voyage in space yet as a single space flight, but you can see that we're getting up there in numbers. So over the next few years, you should look out for these long-duration space flights on the space station to ramp up closer and closer to 2.5 years in space. Now, in terms of conditions on Mars, the Earth is a relatively massive little ball. The Moon, and so therefore you feel a relatively strong gravity. If we call this 1G, then on the Moon what you would experience is something that's 6 times less. Gravity on the Moon is about 17% of what it is on the Earth. So let's say you weigh 100 pounds on the Earth. Well, first of all, consider yourself lucky. But second, on the Moon, you would feel that your weight is only 17 pounds, which explains, of course, why the Apollo astronauts were hopping around quite easily. If you go to Mars, gravity is 38% of what it is on the Earth. Okay, it's 0.38 G. So again, this 100-pound person would feel that he or she weighs only 38 pounds on Mars. I've always said going to Mars is a good weight loss program. Okay. Now, from an engineering standpoint, I have on the left here the good things that are sort of working in your favor if you're planning a trip to Mars, and on the right, the bad things. What's good is that the day on Mars is 24 hours and 37 minutes. It's a sheer coincidence. There's no mystery to this. I don't know about you, but I could use 37 more minutes per day to wrap things up. There's plenty of water on Mars. NASA has a press release usually once a year, usually in September, right, as the fiscal year gets renewed, announcing a discovery of water on Mars, okay? We've known that there is water plentiful on Mars for a long, long time. It's mostly in the form of ice. There's a little bit in the form of vapor and a tiny bit in the form of liquids at the surface, okay? The liquids, incidentally, are possible because it's not clean water, it's super salty water, and not with table salt, unfortunately, but with perchlorates. We'll get into that in a second. Gravity on Mars, we mentioned that. That's better than none. but it's less than on the Earth. On the right, from top to bottom, I've listed here 5 causes of death on Mars in chronological order of cause of death. So let's say you were exposed unprotected without a spacesuit to the Martian environment. These are the things that would kill you first. Okay? First of all, it's the low atmospheric pressure. Within seconds, the gases that are inside your bloodstream right now would bubble up. It'd be like popping a can of Coke. All of a sudden, you release the pressure. The gases that are dissolved in the liquid would fizz. You would fizz to death. This will take a few seconds, and incidentally, it would be very painful, cruel, and unusual. All right. If that didn't kill you, the toxic atmosphere will. You cannot breathe the Martian atmosphere. It's made of CO2. 95% of it is CO2. There's no free oxygen like on the Earth, none at all. And so you would die of hypoxia, lack of oxygen, and also of carbon dioxide poisoning. If that didn't kill, and that would take care of you in a matter of minutes. If that didn't kill you, then the temperatures would. The average temperature on Mars is minus 80 degrees Fahrenheit. You can protect yourself against such temperatures, okay? But if you were exposed unprotected to them a few hours, and then you are completely frozen, and you would die as a popsicle. Then you have the dust. The dust is really very bad news. There are 3 things that are bad about the dust. It's very fine-grained, so it's going to lodge itself in the pores of your lungs. So it's going to mechanically block the pores of your lungs. That's silicosis or Miner's disease. Over time, you lose your breathing capacity. Number 2, the dust is very abrasive because most of the rocks on Mars are volcanic basalts that are crushed by impacts. So you have essentially shard-like dust grains that are very abrasive. And so in contact with your lungs over time, they would tear the tissues of your lungs. You would have mechanical abrasion of your lung tissue. And then the dust is chemically toxic. We now know since 2007 that it's made of, that it contains perchlorates and peroxides. Perchlorates in particular, we use perchlorates as rocket fuel, sometimes also as pesticides. Perchlorates are rich in oxygen and chlorine. They will attack your thyroid. Mark Watney in The Martian should never have brought Martian soil into the cabin where he was living to grow potatoes, okay? Because he would have exposed himself to very toxic Martian soil, and the potatoes themselves would have been toxic, full of perchlorates. No amount of pooping in the Martian soil will get rid of the perchlorate issue, okay? But more importantly, if he had been such a good botanist, he would have known that you can grow plants, including potatoes, hydroponically. You do not need soil. You just need the poop and some water, okay? But Andy Weir is a great guy. He's actually a neighbor of mine in Mountain View. We know each other very well, and we're good friends. But somebody's got to tell him. And then the radiation. The radiation, that's mostly galactic cosmic rays, solar radiation, solar particle events. Very nasty. You're exposed to that at the surface of Mars. On Earth, we're protected by 2 things, a thick atmosphere and a powerful magnetic field. The Earth is like Starship Enterprise. The shields are up, okay? Well, on Mars, there's no magnetic field and only a very thin atmosphere, therefore, no serious protection from space radiation, other than the ground itself below you. So why would we even go to a place like this, okay? It's a godforsaken place that could kill you in seconds. Well, to me, this is the reason. It's a scientific reason. On the left, you have the tree of life on Earth. All forms of life that we know of on the Earth is genetically related. We all use and share some fraction of our DNA, and we all use DNA. There's no form of life on Earth that does not use DNA. And this is something that's really remarkable. This chart on the left, called the tree of life on Earth, is technically not showing you DNA relationships, it's showing you 16S RNA, but it's essentially the same thing. It's the fact that the closer you are to another branch of Earth life here, the more you share in common genetically. So the eukarya at the bottom are the more complex forms of life. The archaea and the bacteria are the unicellular, simpler forms of life. But nevertheless, from us down here, Homo, you might see this, all the way to E. coli, which is one of the bacteria, we all share DNA in common. And the interpretation, the ready interpretation of this is that we all spring from a common microbial ancestor whose nature we no longer have a record of. It might be just too old or somehow too deformed in rocks that might have trapped it. And we therefore have no knowledge now of what this initial form of life on Earth might have been. The idea of looking for life on Mars is to find an example of an alien form of life. This is what we want to find, an alien form of life. Because there's actually a chance we could find Earth life on Mars. Earth and Mars are not isolated. Meteorites come from Mars randomly. When Mars is hit by asteroids or comets, they kick off Mars rocks. Mars rocks travel to Earth. You can pick them up. We've got them in our museums. There might even be one in this museum. So therefore, you can imagine life starting on one planet and being transferred, exported to the other. Life could have started on Earth, being exported to Mars, or vice versa. We could all be descendants of some Martian microbe, okay? It's part of the trade space, even though it's not likely. What we're looking for, however, when we go to Mars is more than just finding life. We're looking for an alien form of life, something that either would not use DNA or would use DNA in a way that is completely different from the way all Earth forms of life use DNA. And so, to me, this is the exciting challenge of the search for life on Mars, is to try to find something that does not plot onto the tree of life on Earth. And therefore, we have to find something that's still living on Mars, because you cannot do genetic analysis on something that's fossilized, okay? Which makes me often say, and it's not a very popular view at NASA, that as long as we keep looking for fossil forms at the surface of Mars, even if we found them, it would be very exciting. We would say, hey, we found some form of life on Mars that existed once. We would not be able to tell if it's alien or not. To determine if it's alien, we got to go after the real Holy Grail, which is living life on Mars today. So how do we find living life? On Earth, all Earth life needs liquid water. And everywhere on Earth where there is liquid water, there is life in it, if the water is clean. The good news is there has been liquid water at the surface of Mars throughout Martian history. You can see ancient riverbeds on this ancient terrain on Mars. You can see these little finely chiseled gullies on the slopes of crater walls and canyons on Mars. So therefore, liquid water, even though I'm of the view that there has never been really huge amounts of it at the surface of Mars, that's a growing opinion, I have to say, but nevertheless, throughout Martian history, there's been some liquid water near the surface of Mars, and that's very important because of this connection between Earth life and liquid water. So NASA's strategy to find life on Mars, to look for life, is to go to those places where there was once water in the past or where there might be water still present today. We haven't done the latter yet. We haven't targeted places where somehow we would be looking for liquid water that's present on Mars today. And I think that's actually what we should be doing. The places to go for that would be places that are sheltered from the surface, inside Mars, where it's still warm. Okay? For example, in lava tubes on the flanks of some of Mars's volcanoes. Mars has fantastic volcanoes. This is my favorite. Might be yours too. Olympus Mons. It's, I'm showing you at the bottom here the profile of Olympus Mons compared to Mount Everest. That little black triangle is Mount Everest. Okay? Olympus Mons is this towering pile of basalt that's sitting on Mars. It's lava flow upon lava flow. And to build such a large volcano on Mars, it must have been active for the bulk of Martian history. And because of that, chances are it is still active today. It's just not erupting. It's probably dormant. But wouldn't it be fantastic if all of a sudden Olympus Mons woke up just like Mauna Kea or one of the Hawaiian volcanoes wakes up every now and then to some lava fountain. Okay, so this is the type of volcanism that we'd be looking at on Mars. And again, right now we don't know if there are even hot spots along the flanks of this volcano, but it's the type of thing that upcoming missions might be able to tell us. And so if we could enter the volcano, go to places that are cozy, dark, well, protected from radiation, and yet moist and warm, maybe we'll have a chance to find living life on Mars today. So these are two prospects for finding living life. On the far right, just drill deep. And if you're doing this near the equator, where actually you have to go pretty deep before you find liquid water, the deeper you drill, just like going down a mine, the warmer it gets. At some point, you get to the melting point of water, and it's estimated that at a depth of about 2 to 5 kilometers, which is similar to what we do for oil drilling on Earth, oil and gas, you will get to liquid water on Mars. The alternative is to maybe be a little more clever and to look for openings, natural openings in the ground of Mars, like this entrance to a lava tube. This is an actual picture here at the top on my left of an entrance to a lava tube on Mars. Okay, it's a skylight. It's a collapsed lava tube roof. And so I think it's an amazing picture. Imagine what might be lurking inside in the warmth and coziness of this lava tube. Okay? And at the bottom, I'm showing you a lava tube that's on Earth, just to show you that you can actually have a whole ecology going on there in these little places. So why go to Mars? I just gave you my favorite reason, which is science, but over the years I've compiled a laundry list of reasons to go to Mars. But the bottom line is none of these matter, and I don't have time to go through the details. None of these matter because the reason why nations explore and spend big amounts of tax dollars to go on exploring expeditions is only when it serves the national strategic interest. And here are just some examples. President Jefferson was a scientist. He was interested in botany and wildlife, but that's not why he sent Lewis and Clark out west. He sent Lewis and Clark out west for big bucks, by the way. That was the Apollo program of its day, okay, because it was in the national interest at the time to know who was living out there, who we could trade with, what were the navigable routes, what were the trafficable routes. Okay. It was of strategic interest for us, if we were living on the East Coast, to know who was out west. Same thing with President Kennedy. We did not send Americans to the moon in the mid-60s because all of a sudden we were interested in lunar science. It had zero to do with science. It had all to do with beating communism and the Soviet Union at something. The Soviet Union was ahead of the United States at the time in space, and we had to do something that was difficult enough to do, far enough in the future to have a chance to catch up. And sure enough, that was putting a man on the moon and returning him safely to the Earth. And so that is why Apollo was done. Of course, once you've committed to going to the moon, once you've committed Lewis and Clark to going out west, of course you're going to do science. Science becomes the opportunity. It is sometimes what dominates your activity at the site. On the moon, we didn't open a bank branch or a law firm. We collected moon rocks. So we did science. But it's very important to distinguish what drives your surface activity, okay? I mean, what's dominating your surface activity from what's motivating your presence. Two entirely different things. And just to push the analysis one step further, even today, the National Science Foundation spends about $2 billion a year in Antarctica, okay, every year. Overall polar programs. Well, it has nothing to do with science, really. Okay? Congress agrees to spend $2 billion of taxpayer dollars each year because it's in the national strategic interest of the United States to be in Antarctica. There are other nations there. It's a geopolitical free-for-all at some point. There are resources to be mustered at some point. We've got to be there because others are there too. And in fact, we have some very strategic positions in Antarctica. We've got the South Pole Station, McMurdo, and a few others. Okay. Now, of course, once you've committed to being there for geopolitical reasons, what you're going to do is science. And excellent science is being done by the NSF in Antarctica, but it's not the reason why we're there. There goes my NSF funding. Okay, so why would we go to Mars? Well, this is showing you the years of last century on the x-axis versus the number of graduate degrees awarded in US universities, masters and PhDs. And we're looking at 4 fields of science: Earth, atmospheric and ocean sciences at the bottom, math and computer sciences, physics, and engineering. First of all, you notice that all 4 fields of science are increasing essentially exponentially from left to right. That's due to population increase in the United States. The overall population of the country is increasing, therefore there are more and more degrees in the sciences that are delivered. That makes sense. But what's remarkable is the doubling of graduates in math, computer sciences, physics, and engineering during that narrow window of the Apollo program. The Apollo program enthralled an entire generation of young people. It drove them to go into science, technology, engineering, and math. Okay? This was the greatest benefit of the Apollo program, and I'm saying this even as a planetary scientist, was not what we learned about the moon or the history of the Earth-Moon system. And of course, beating communism was something that served its purpose at the time. But the greatest benefit that we're still riding on today is the fact that we created a generation of STEM-capable people in this country. And California here, and the Bay Area in particular, okay, is where we have the headquarters of this STEM force. We've got the US Air Force, you know, helping us with safety in the skies, the Navy, okay, the Army on the ground. But let's not forget the STEM force, which is helping us with our economic and technological edge, okay, around the world. And this is something that was built on the Apollo generation. Okay? Jeff Bezos will tell you that he was inspired by Apollo, and so was Elon Musk. Okay? And sure enough, they're doing space stuff. So, going to Mars would do the same thing. Okay? I would say that returning to the moon doesn't quite cut it because we've done it. Going to Mars would create a new spike in our competency, will create a new generation, a new STEM force for the next generation. China, not too long ago, landed a robotic rover on the moon. We poo-pooed that because we did that more or less 50 years ago. Within the next 10 years, China will land a Chinese cosmonaut, astronaut on the moon. And we will poo-poo that because we will have done that 50 years earlier. But we would be missing the point. We would be missing the point because right now, as we speak, there's an entire generation of kids in China, okay? Hundreds of thousands of kids who are completely enthralled by China's space lunar program. And they're going into scientific fields and creating a STEM force in China. Okay? So nothing wrong with working with China as far as I'm concerned, but the point is if you care about what's going to be competition in our future or how we might position ourselves globally in technology, that's something to think about. So how will we go to Mars? Well, you need a big rocket because you've got a lot of things to take with you since you're gone for a long time and you're going far away. This giant rocket, when it flies, will be the most powerful rocket ever flown. It's called the Space Launch System. It's being built as we speak in Alabama, in Huntsville, but also at Stennis in Louisiana. The SLS will come in 2 versions, a crew version that's somewhat smaller than the Saturn V, and the large cargo version that's at the far right there. Okay. The first test flight of this rocket is slated for late 2018. I don't know about you, but I plan to go to the Cape to watch this. If it's successful, it's going to be spectacular. If it's not, it's going to be spectacular. Okay, but how does this work? To go to the moon, you needed 1 Saturn V rocket to send 3 people to the moon and bring them back within a week. For Mars, this is a typical scenario. In total, you're going to need 7 of these SLS rockets. 6 of the cargo version, 1 for the crew. Okay. Step 1, you launch 4. Of course, you never align them all at the same time. But step 1, you launch 4 of these giant cargo rockets. They assemble 2 large spaceships, that's step 2, in low Earth orbit. These are cargo ships. There's nobody on board. And what you're going to do is send 2 cargo ships to Mars ahead of time, 2 to 4, maybe 6 years ahead of time, okay, so that you're not traveling with stuff that you don't need to travel with. For example, you don't want to be going to Mars with the house you're going to live on Mars, the house you're going to live in on Mars, or the cars that you're going to drive on Mars. For one thing, what if they don't make it properly? Then you're left without a car or without a house on Mars. So all this stuff that you don't need to travel with, but want to make sure that you will have on Mars once you get there, you're going to send ahead of time. Okay? So you're going to pre-position a bunch of assets on Mars ahead of time. Once you know that it has all landed safely in the right place and in the same place, and it's still working, then you send 2 more of the large rockets to low Earth orbit. They put together your spaceship, which in this scenario has an inflatable section there at the front. That's the giant space marshmallow, also known as the astronaut bouncy house. Okay. And then once that thing is assembled in low Earth orbit, then you and 6 other crewmates, so this is a scenario for a crew of 7, you launch in the final smaller SLS rocket, you dock with your spaceship, you make sure every switch works, and then you leave for Mars. So that's a section of the front. I don't have time to go into all the details. I will comment, though, on the fact that if you look at the inflatable habitat here, the walls align with what look like sandbags. And of course, they're not sandbags. They are actually bags of water and food. The reason why you want to surround yourself with water and food is because both water and food contain hydrogen, and hydrogen, as it turns out, is a very good dampener of space radiation. Okay? And so there's good news and bad news with that. The good news first. You're thirsty, you drink the water, you go to the bathroom, it pipes the urine into the service module, it cleans the water, it recycles the water, the urine, and it goes back into a clean water bag. So we're already doing this on the space station. We're recycling astronaut urine and sweat every day. You cannot take on a 2.5-year mission to Mars fresh water for every day for 7 astronauts. That's too much water. You can only take so much, and what you'll do is, of course, recycle it as you go along. In fact, a few weeks into your trip to Mars, you are drinking each other's recycled urine and sweat. Now, that's the good news. The bad news is food. Food, you can of course have food bags with your name and your favorite food inside, okay? But what happens after you eat? You go to the bathroom again, and now you have poop. You cannot recycle poop. NASA's not even trying. If you were to write a research grant at NASA to study the recycling of solid waste from humans or any animal, you would be rejected, because we know since from many studies in the 60s and 70s that it's extremely difficult to do. Okay, in fact, you need a whole biosphere. So we cannot recycle poop. So what are you going to do with it? You cannot open a window and just toss it out into space. First of all, no window opens. Second, you don't want to pollute space. So what you do is you collect it. And the reason why you want to collect it is because your poop is still full of hydrogen, and deep space is such a resource-poor environment that you have to consider even human solid waste as a resource. It's radiation shielding. So the poop is collected in a Ziploc bag, emphasis on lock, and that bag goes back on the wall where you took the food in the first place. Okay? I recommend very careful labeling. Now, we're laughing perhaps at this, but why don't we do this on the space station? Well, first of all, because we don't need to. We have supply cargo ships going up and down all the time. Number 2, the space station is not really exposed to the kind of radiation that a deep space mission like this would be. Because the space station, even though it's above the Earth's atmosphere, it's still well inside the Earth's magnetic field. And so it's actually protected substantially from space radiation, unlike people who would be going out to Mars, okay? So if you go out to Mars, you're going to have to start doing this. All right, the big day comes. You are in orbit around Mars. All 7 of you cram in the little pod in the front of the spaceship. It's the Mars lander. You enter the Martian atmosphere. The parachutes open, if you're lucky. Then you jettison the heat shield. Then you jettison the parachutes for a few seconds. You drop like a rock. And then the retro rockets come on, if you're lucky, and you cushion your landing. At this point, you are tightly packed like sardines in a tiny little pod, okay? This is not your habitat on Mars. Hopefully, you've landed right within walking distance from all these other assets that you've sent to Mars several years ahead of time, okay? Now, I promised my publisher I wouldn't show every page of my children's book, but she's not here, so. Anyway, this is a cartoonish depiction of the inside, but just to point out a few interesting features, in this scenario, you have a 3-deck habitat on Mars, and what you will have to deal with is sort of a gradient in cleanliness. Okay? The lower deck will be where you repair spacesuits, where you analyze rocks, where you drive and repair vehicles. It's going to be the dirty deck. Then you have the mid-deck where you might just have your normal living space, kitchen and lounge. And then at the very top, quarters that you're going to want to keep very clean, almost aseptic. You'll have your sleeping quarters where you're going to spend many hours a day sleeping, and also your computers, okay, with a control tower type setup at the very top. And notice the water tanks at the very top, because you still want them to shield you from some radiation at the surface of Mars. So how are we going to explore a place like this? Well, there are many places that we can go to on the Earth. One of my favorite ones is this one. It's Devon Island in the Canadian Arctic. It's about 1,000 kilometers from the North Pole. Devon Island is the largest uninhabited island on Earth. When you're on Devon Island, you are the population of Devon Island. It has a giant meteorite impact crater called Houghton Crater, and we've been going up there every summer for the past 20 years. I've lived in California for 20 years. I have yet to spend a full summer in California. Okay. Devon Island is an amazing place. It's really barren. Well, there you go. It's like this. There's hardly any visible vegetation. There is life, but inside rocks. Otherwise, it's a godforsaken place. We have a base camp that we operate, and it's teaching us some lessons about how we might operate a base on Mars in the future. But more importantly, we're learning how to use vehicles and spacesuits to explore Mars. What procedures work best? What team sizes work best? How much time do you need to explore a certain area? How many rocks do you end up collecting? What is your sample processing capability or requirement going to be? So let's talk about just two things, spacesuits and rovers. This is the state-of-the-art for spacesuits. Okay, it's the Space Shuttle EMU suit. It weighs 300 pounds on Earth. Thankfully, you don't need to wear one to survive on Earth. If you take it to low Earth orbit, where you are weightless, essentially, it is weightless. The suit does not. The suit has the bulk and, of course, the inertia of a 300-pound suit, but not the weight of a 300-pound suit. If you take this suit to the moon, not that it's really designed as a walking suit, but let's say you took it to the moon, with gravity 6 times less, it would have a felt weight of 50 pounds. That's quite manageable. That's like a heavy backpack. But if you take this suit to Mars, it would have a felt weight of 125 pounds. Okay, way too heavy for you to do field work, for you to be an effective explorer. So we face a real challenge, and those of you who are contemplating a career in aerospace engineering, I would encourage you to go into the spacesuit business. Okay? We need to cut the mass of this spacesuit in half. We have to cut the mass of the spacesuit in half so that by the time it goes to Mars, a 150-pound suit would have a felt weight of only 60 pounds. Okay? And that's a big challenge. Where do you trim the mass of the spacesuit? A spacesuit, you have to realize, is not just clothing, of course. It's a wearable spacecraft. It's got life support systems, computers, communication systems, waste disposal, coolants, warming pads, all kinds of complexities. Okay? It's a real spaceship. So we've been working on creating a Mars spacesuit with Hamilton Sundstrand, the company that develops spacesuits for NASA. And in addition to needing to be lighter, it also has to be able to withstand dust storms. Here we are testing some of the fabrics in a simulated Martian dust storm. For that, you use Hawaiian volcanic ash combined with kitty litter. This is true. We also need a suit that can allow us to tackle severe terrain. You want to maybe rappel down some canyon walls to look at rock layers. This is frowned upon by the astronaut office, but geologists love this. In any case, we might end up with a suit looking like this. Blue, why? Because it's the complementary color to orange, so it's what would keep you more visible on Mars. Thick boots to handle rock and sand, gaiters to protect your lower legs. You don't want to puncture your suit. Notice there's a smartphone device on your wrist. The Apollo astronauts actually had a little binder, a spiral binder on their wrist to serve as a checklist. Here you would have a little digital display. You could also take selfies with it. And then this is a rear entry suit. So you enter the spacesuit from the backpack. The backpack swings open like a refrigerator door. You climb in, feet first. Your feet go all the way down to the boots. Then you put on your headset. Then you insert your arms. Then you close the backpack behind you, and now you're sealed, and off you go. Okay. So we've been taking our concept suits out to places that are sandy, like the Viking 1 landing site. For example, to Dumont Dunes in California. So what you got to look out for are, of course, unstable slopes, but also people riding ATVs like bats out of hell. Now, speaking of ATVs, we also need to get around. You can only walk so far on Mars. In fact, walking will really not be the way to go. You want to be able to drive as much as possible and then take a few steps really to collect rocks or to hammer at something. Okay, so on the moon we had this two-person open-seater, which was just fine for short distance and short duration lunar excursions. But for Mars, we're looking at a longer stay. Each astronaut is what we're advocating. Each astronaut will have his or her own ATV, all-terrain vehicle, okay, a quad bike like this. Electric, of course, maybe powered by nanocells, maybe powered by fuel cells, more likely nanocells. This is, in fact, a concept that we've come up with from our work in the Arctic, which is the idea that the astronaut explorer is no longer just this person with his or her spacesuit, but it's the astronaut, the spacesuit and the rover, the ATV. That's the exploration system. And now, with this ATV, you can offload some of the heavier elements that are in the backpack of your spacesuit. You don't need big batteries anymore in your backpack. You don't need large oxygen tanks in your backpack if you can have spares on the ATV. So while you're riding, you recharge your small oxygen tanks in your backpack. You recharge your batteries so that when you step off of this ATV to go collect rocks, you're walking on with a lighter spacesuit. Okay, so, and of course, this ATV is not going to stay behind. It's intelligent. It's smart. You can talk to it. It will follow you. So you have to think of yourself stepping off of this thing and having it follow you like a dog, like my dog maybe, and that way you don't have to carry the rocks all the way back to your ATV. You just turn around. It's right there for you to do that. Okay. I got to move. So next summer, we'll continue our tests on Devon Island with my dog and the spacesuit people. Now, for longer road trips, we want the motorhome approach, okay? The pressurized rover. So now you're living inside in shirt sleeves, and you put on a spacesuit only to go outside. I've actually been lucky enough to be the first scientist to test drive this thing in Arizona a few years ago. It's an amazing vehicle. It's a concept vehicle for pressurized rover for the moon and Mars. The wheels can turn independently, so you can actually do a full, complete circle right over the center point there. And it's not even a U-turn, it's a turn on the spot. It's very easy to drive. If you're right-handed, you sit on the right. If you're left-handed, you joystick it from the left. To go forward, you push. To go backwards, you pull. To turn on the spot, you twist. This is when all those hours of video gaming finally pay off. Okay, the movie The Martian. This is wrong for several reasons. First of all, for a pressure vessel, it should not have sharp angles. Okay, it's just like your propane tank under your barbecue is round for a reason, to spread the pressure evenly. You don't want an angular vehicle that's going to be bumped to hell on the Martian rocky landscape, okay? And so you want a rounded shape. But second, this guy is depressurizing. This rover design makes you depressurize the entire cabin every time you go in and out of the cabin, right? The door opens, so all the oxygen that's filling the inside of the cabin is lost to the Martian atmosphere, and then that's not very efficient. Also, you're climbing in and out of this rover all the time with this dirty Martian spacesuit full of Martian grit. Remember, the dust is toxic, so you don't want to be doing that. Okay. So instead, you should do this. All right. This is a design that NASA has come up with where the spacesuits are kept outside at all times. They're dusty, they're gritty. There's no reason to bring them inside the habitat of the cabin of the rover. And to go in and out of your spacesuit, you can enter and exit your spacesuit directly from the inside of the vehicle through the backpack. The backpack door opens into the inside. You climb in and out directly from the inside of the vehicle. But your spacesuit stays outside at all times. This is astronaut Rex Walheim demonstrating this. And you can see that all he needs to do is do a little chin up with that bar at the top. And for those of you who are concerned about doing this on the Earth, don't forget you're in Martian gravity, so it's easy to do. Okay. This thing can drive itself at night. So let's say you explore a place during the day, and you're done. You climb back inside. You get out of your spacesuit, of course, before that. You cook dinner. You write a report. You go to bed. You draw the curtains. And while you're sleeping, okay, this thing rolls along on Mars, either on its own or teleoperated from with the time delay by mission control. And the next morning, you're at the edge of a canyon, and it's a new day to explore. So on Devon Island, we are simulating some of these scenarios with Humvees. We had this red Humvee at first, but then we were tending to get it stuck just like Spirit on Mars here in sand or mud. So we got another Humvee donated to our project. This time we decided to drive it all the way to Devon Island in the first place. We drove the Northwest Passage. It took us 3 seasons to complete the journey. Tucker mentioned to you this movie that we filmed during the expedition. It's called Passage to Mars. It was a labor of love, the expedition that is, and the film as well, I guess. But anyway, it's available on DVD and online. So when will we go? Well, between now and 2024, the space station will continue to be used. Congress just had a hearing about using the space station beyond 2024, so no decision has been made yet. But the Russians have already announced that they're pulling out in 2024. Up until now, NASA was on a path to possibly go do some asteroid exploration, but the plans are now shelved. And the current thinking is that we will be going to Mars, but probably with a return to the moon somewhere along the way. And I think that returning to the moon is something that's going to be very hard to not do, mainly because other nations now and other entities are going to the moon. So it's a place where somehow NASA will have to have some presence on behalf of the United States. But the other thing is that the Apollo experience is really fading. A lot of the expertise in space expeditioning and these types of missions has now long retired and, in fact, died out very much. And so the truth is we did not go to the moon. The generation before us went to the moon. And so there's a lot of things that we might want to learn again to do properly in terms of surface operations before we head back to the moon.
Ladies and gentlemen, join us once more in African Hall to hear from NASA's Chris McKay about the future of human space exploration, starting in 10 minutes.
Okay, so I'm gonna wrap this up. 2030s, the moons of Mars, because going to Mars orbit will be quite a bit more doable than going to the Martian surface. 2040s, humans on Mars. And again, that's the NASA schedule, which I think is reasonable. There are wild cards, SpaceX, Blue Origins. SpaceX might be able to attempt going to Mars in the late 2020s, which would be very exciting. We can talk more about that. A very exciting development in this whole business was the fact that NASA, about a year and a half ago, convened the first ever workshop to start selecting the first landing site for humans on Mars. Those of you who lived Apollo might remember how excited people were when the first workshop was convened to pick a lunar landing site. The same thing happened for Mars just about a year and a half ago. 50 sites were proposed. I'm leading a team that's suggesting Noctis Landing that's circled here. NASA has not narrowed it down at all yet, okay? And we're going to keep those in play for quite a while, I think. Noctis Landing is great because it's both near the canyon so that you can look at the fossil record, the road cut on Mars, if you will, and it's also near the volcanoes. So who will go? And I'm getting to my last slide. Who will this person be? Well, the crew size, 5 to 8 people, we think. Beyond that, you're looking at doubling the rockets, and it spirals out of control very quickly. Crew selection criteria. Well, would you have a gender mix? Should you have an ethnic mix? Should you have an international mix? Should you have a marital mix? The 4 first ones that I just listed, okay, are important considerations. They are about sending people, a crew that would be representative of all of humanity. So in that sense, it serves a societal and in some respects, a political role as well. But it has little to do with the actual performance of the crew. You can imagine a crew that has a marital mix that would work. So a marital mix meaning married couples forming the crew. You can imagine a crew made of married couples that would work very well, and I could certainly imagine one that would not on a 2.5-year journey to Mars, okay? Plus, on a crew of 7, you'd have 3 married couples and then the 7th person. Okay, but what's sure is that you will have Renaissance people. Each person will have to come with more than one set of skills, in fact, several skills. You're looking for jacks of several trades, aces of several trades, not a jack of all trades. Second, because each crew member will have many skills, in other words, they will have gained expertise in for example, the medical doctor would need to be a surgeon, but might be the biologist as well on the mission, and maybe have training in dentistry as well, and possibly in fixing spacesuits, okay, which have a lot to do with physiology. Well, to be an expert at all these things, you need many years of training. So most crew members will likely be seasoned astronauts. Unlike in the movie The Martian or the book, okay, Martian crews made of young people are unrealistic. You're smart enough when you're young, but you just haven't had time to become expert enough at many things. It just takes time to build. It's the 10,000-hour rule, right? So the average age of a crew member going to Mars, I'm guessing 55, 60 years old, okay? There might be a token young person on the crew, just to have somebody to make fun of, but the truth is, just look at a shuttle crew or space station crew, mostly middle-aged people. Redundancy, you need to have a redundant crew. And I just illustrate this point about redundancy. This is a Soviet Antarctic mission from 1961. There was only one surgeon on the crew. He had to do an appendectomy on himself in the middle of the winter, so local anesthesia. He's operating on himself to extract an appendix, okay? And the part that I find sort of amusing is he did recruit one technician on the whole team to help him, and that was the meteorologist. So you don't want to be doing surgery on yourself with just a meteorologist there. You want to have somebody who's had some medical training as well, okay? So redundancy is important. So these are the 5 qualities that I think a crew member must have. Be knowledgeable, be healthy, be really motivated. You're talking about giving up not just 2.5 years of your life to go to Mars, but 10, 20 years of training ahead of that, and maybe not go. You have to be adaptable, tolerant to change, tolerant to stress, tolerant of others. And above all, you have to be altruistic. You have to be a really good team player. It's not about you, it's about the whole planet. All right, thank you.